Yeah, I would really appreciate if people are a bit chatty, it's incredibly boring to just listen to my own voice here. Okay. All right. So, uh, welcome to the course. There are a few things to be mentioned about how this course is going to proceed. So, I'll do that now, and then we will have a short introduction to what this subject area is, and then we will start with the technical stuff on Thursday. Okay. So, what I want to let me just make this full screen. Sorry. So, as you might already be aware, also since you are the generation that uses this right from childhood, computer vision is essentially that branch of artificial intelligence which deals with the problem of achieving vision in a machine. Okay, so we will look into some depth about in depth into what vision means. Okay, so what you want to understand is what is the difference between digital image processing, computer graphics, and computer vision. So if you have read anything in these areas, then you might have seen the same kind of words appearing in all these. Okay, so let me sort of spend 2 minutes talking about what is the difference between these three things. So digital image processing is the process of manipulating a digital image using some algorithm. Okay, so this is typically what you would do on Adobe Photoshop. Okay, so or in you can do this in many other softwares also. Okay, so where you do simple things like some kind of edge detection or filtering. Okay, or some kind of feature detection, or even simple stuff like geometric operations, transformations like rotations, cropping, even that. Okay, so that all comes under digital image processing. There is much to it, and we will be talking about this in the course. Okay. In computer graphics, you actually deal with a problem that is the opposite of computer vision. Okay, so computer graphics, what you want to do is you want to emulate using a computer what you see in real life. Okay, so you want to emulate real life images and movements on the computer. So this is where animation, graphics design, or surface visualization, machine design, all these things come in. Okay, so computer graphics is more like a creative field. Okay, uh, computer vision, on the other hand, is the opposite. So in this, you don't want to emulate what you see in real life, but what you want to do is you want to, from the 2D image or from videos, you want to understand what it was in the three-dimensional world. Okay, so from an image, you want to understand the contents of the image, and you want not just to understand as a human, but you want the computer itself to understand. Okay, so you want to give the computer an image, and you want it to spit out uh, a statement about the content of the image. Okay, so that is essentially what computer vision is about. It's about perceiving what is in the image. Okay, by itself, or working towards algorithms that will help the computer to perceive by itself what the contents of an image are and make intelligible statements about it. That is what computer vision essentially deals with. Okay? Full scene understanding, that's what it's called. So for the course itself, I would say the prerequisites are a strong background in linear algebra, because you will see everything is linear algebra here. And of course, some basic geometry also. Uh, then Python, you should be, for doing anything with this knowledge, you need to be able to program. And while MATLAB is also a very preferred language in computer vision, it's not free and maybe it's not available to everybody. So we will stick with Python, which also has a lot of useful library and integrates OpenCV. Okay, so Python, you should be very comfortable with programming in Python. Machine learning, I expect that you have done machine learning, and minimum background is machine learning. And if you have done advanced machine learning, that is even more preferable, because then you have already seen perceptrons and you have already seen CNNs. Okay, so that will come in handy in the course. But if you have not done advanced machine learning but have done machine learning at least, then those things you can pick up on the way. Okay, so uh, I would say the minimum requirement is machine learning. Any questions here? Okay, so the syllabus for the course, sorry, why is this going ahead? So syllabus for the course, I'm saying more or less because it entirely depends on how much we can cover. Okay, uh, so computer vision, I mean, this topic is huge, and there's just new things being added to it every day. Okay, so it is impossible to cover everything that is up to the state of the art today. So that we cannot have that as the aim right now. And even in the syllabus, so there are different views that one might take. One might want to spend more time on the mathematics of it, or one more time on the programming part of it, or more time on the applicability or application of it. Okay, so there are various views that one can take, and in that sense, it can go in various directions. Since I'm going to focus on the applicability, uh, or when you want to actually apply or design a computer vision pipeline, then what are the things that you will require to do? So that is going to be the focus of my course. So, and then in even that, there are many topics in digital image processing that need to be covered. So that is why I'm saying more or less we'll see how much we can cover. But I'm listing here the topics that I would like to cover. So first, I've divided this into 4 parts. First part is image formation. So image formation is where you learn the basics of. So there are two things in image formation. One is the geometric image formation, which is your pinhole camera model, uh, or your ray optics, that kind of thing. So you need to have a basic understanding of ray optics and your pinhole camera model. And there is photometric image formation, which means how is image formed in a camera. So for this, we also need to study some camera basics. How is an image? What is the process of when you click an image? What is that entire process of the object being captured as an image on the sensor and being available as a JPEG image, a JPEG file to you? Okay, so this entire process, this is what covered in camera basics. And then one has to take a little bit of, not too deep, but a little bit of dive into the mathematics behind this whole process of converting the information from a 3D object to a two-dimensional image. So for that, we will look at the mathematical modeling of perspective and what's called as a camera matrix, which means the parameters that come into play when this transformation is done. Okay, so that's the camera matrix, and then the process of camera calibration, which means that if you have a camera on hand, okay, so some of you might be interested in photography, so you might have some fancy cameras, or you might just have your mobile camera. Okay, so if you have any camera in hand, then without opening up your camera and checking the sensor and everything, okay, or actually computing the distances between the lens and the sensor, all those things, is there a way of telling all those? What are these numbers? What are these distances? Or what are the parameters in the camera matrix? So that process is called camera calibration. Okay, it is also useful for a number of other things. Like if you take an image and there is some kind of distortion appearing in the image, then the knowledge of the camera matrix helps you remove that distortion. Okay, so these transformations that can be done in an image to improve its quality, make it as close to the uh, as possible to the ideal image. Okay, so all this can be done if you can compute this camera matrix, and that process is called as camera calibration. So we will take a look at that. Uh, yeah, and then some basic geometric transformations that you can do, and this problem of estimation. We will talk about the estimation problem, but I don't know how much we can go into. But if anybody is more interested in this kind of mathematics, I can provide you some good references. Okay. Now, from once you know what how image formation happens, then we can start talking about vision. So in vision, generally, it is divided into three levels. Okay. The low or early level vision or early level process, mid level, and high level. Okay. So this is just some kind of nomenclature to make it when one is designing the process to understand what level of steps are being involved. Okay, but low, mid, or high has nothing to do with the importance. I think all three are equally important. It's just to do with the difference in what is your input and what is the output. So in a low level process, your input is an image, and the output is also an image with some you have worked on the with some pre-processing now. Okay, you have probably removed noise, or you have probably detected the edges, or you have segmented it. Okay, segmentation even will go to mid, but you have rotated, suppose, or you have cropped. These are definitely low level. Okay, or you have filtered it in some other domain. Okay, or you have convolved it with something. So these kind of processes, these are low level processes where your input is an image, output is also just the image. You are not giving any information about the image. The mid-level processes, on the other hand, will take in the image and give out uh, some information. Okay? So in terms of attributes, which usually means in terms of a vector. Okay, so the output will be probably a feature vector, or it could even be you have given an image and the output is the vector consisting of areas of the objects found in that image. Okay, so that is the output. So these things are called as attributes. Okay, those attributes could be color attributes or object attributes such as size, shape, okay, or maybe corners, edges, anything, perimeter, all these things. So if you give an image and you expect an attribute to be coming out of that process, then that's a mid-level process. And examples of these processes are segmentation, uh, feature extraction, that is what the general thing is called. Okay, corner detection, these kind of things are examples of mid-level processes. And high-level process is when you feed in these attributes and or the original image, and you actually expect some intelligible output in terms of a statement, in terms of some understanding as a human would do. Okay, so if you look at an image and somebody asks you to describe it the way you would describe it, that is what you want your program to do. Okay, so that process is called high level vision. Okay, or comes under high level vision, and the scene understanding and all everything is part of high level vision. Okay, uh, and when one thinks of designing a typical computer vision pipeline, all three processes go into it. Okay, so you cannot say that you're only an expert in high level vision or only I mean, you can only be an expert in low and mid, but you cannot do the third without knowing the first two. So a typical computer vision pipeline looks like this. So there is image acquisition. Okay, so even though you're not involved in the image acquisition process, when you're working on the images, you will probably need knowledge of how the image was acquired. Okay, so stuff like whatever is involved in the image formation that I talked about earlier, camera basis. You will need to know information about the camera with which the image was acquired. Okay, so the process with which it was acquired, on what kind of lighting was there. Okay, were there any external changes being done to the object or to the camera? So various things. Okay, so there is this image acquisition at the first level, whether or not you are doing it. Okay, even if the images are just provided to you, you need to know information about image acquisition. Then there is pre-processing. Pre-processing in this sense. Okay, you could be just some basic noise removal or some addition of or subtraction of images, something basic. Could be something non-basic also. There could be some morphological operations. And there could be some filtering. You're looking at it in the frequency domain, stuff like that. Okay, so all that comes under pre-processing. So what you do in this first step is you prepare the image for the next step. Okay, you prepare, for example, if you want to do segmentation, then you prepare by example, you could increase the contrast. Okay, so that it becomes easier for your algorithm to detect edges. That is part of pre-processing. Okay, uh, then the intermediate level or the mid-level processes are these, where you typically you will have some kind of segmentation to be done, because segmentation is the process where you separate the different objects and background in the image. Okay, and for see, as a human, when you look at an image or when you look at an object, your brain is trained to separate it from the background and look at the object and understand what it is. It does it in a flash so that you don't even realize that you've done this entire process. But when an algorithm is doing this, the algorithm is being designed, you have to remember that you need to separate objects that you're interested in. Okay? That process, so segmentation will typically form a part of any computer vision algorithm pipeline. So segmentation, then there is, as I said, you want some attributes. Some Okay, you have the image, now you need to understand it, which means first you need to understand what are the attributes, what are the uh, or put everything in numbers essentially. Okay, put everything in numbers and vectors so that the machine can process it further. So this process comes in the intermediate level, and then finally you feed those attributes to some, maybe if you're doing a deep learning algorithm, well, you feed your attributes to your uh, neural network and try to get output in terms of some understanding. Okay, if you want a statement, or if you want just bounding boxes, or you just, or it could be an output like this is a face, this is not a face. Okay, or it could be something more like you have 10 classes and this object falls in this class, anything like that. Okay, so conceptual understanding of whatever is in the image, that is high level vision. So this is how a typical computer vision algorithm pipeline looks like. Okay, and now with respect to this, these three levels, what we are going to cover, try and cover in early or low level vision, is all these basic methods that come in image processing. Okay, so these are all basic methods when talked about digital image processing. And mid-level, so here I have, even though I have mentioned just two, segmentation and feature extraction, there are many segmentation methods and many feature extraction methods. So I mean there will be 4 or 5 of each of these. And high level vision is something that I'm not going to cover in class, because from my experience of teaching this last time, reaching up to here itself will probably take us 3 months or so. Okay. Uh, so this is not something that I can do justice in the course itself. So if we like sort of go faster this time, then we can talk about high level vision. At least I'm hoping we can talk about pattern classification methods, if not deep learning. But even then, what I would like you to do is work on a project that will involve high level vision. This is why I require you to have done machine learning before, because any project involving high level vision will require uh, some CNN. Okay, so this high level vision part will mostly be covered by your project. Okay, and the way this, okay, so here are some the text that we will use for low and mid level vision is this digital image processing by Gonzalez and Woods. Okay, is the best available reference as far as I know for this subject. Okay, it is considerably deep and detailed. Okay, and yeah, so but there are some other good books also. Although these two books, the next two, don't really deal with digital image processing. Okay, so image processing is sort of skimmed through, but they deal with more like this multiple view geometry, and this book also deals with various aspects of computer vision, but not in so much detail. Okay, however, uh, these books are good in the sense that they will give you broader perspectives in computer vision. Okay, and there are some topics that I refer to from both these books also. Okay, so when the time comes, I will tell you what sections to look at and so on and so forth. Of course, this book by Deep Learning, which you might already know, is a good reference for your project if you require some theory. And finally, this book by Zaleski, uh, if you Google any computer vision course, this book will be listed as a textbook. But I don't sort of agree that this is a good textbook, in the sense that if you read through this book, you will get a sort of bird's eye view of things, and a lot of references and a lot of information. This book contains a lot of information, okay, about computer vision, its history and methods and everything, and the state of the art. But as a textbook, I don't find it to be suitable for, at least for a course like ours. Okay, so, but yeah, this book is there. I've made it up. It's available online also, by the way, and it is available in the books folder for the course. Okay. But as far as most of the work goes, it will be through this book by Gonzalez and Woods. Any questions so far? Okay, so let me tell you about the course structure and grading. So we will have weekly or bi-weekly assignments, which could be theoretical as well as computing assignments clubbed together. Okay, so now there will be no separate theoretical and computing. So, and computing will mostly be, okay, you write a Python code for something like this. Okay, so that is we mostly bi-weekly. I think weekly will not be possible. Uh, then there will be no midterm, but we will have 4 quizzes. Quizzes on the 15th of each month: February, March, April, May. 13th May is the end of the semester, I believe. So, we could have the last quiz a bit earlier also, or we could keep it 15th, whichever suits us. And finally, project and presentation. So as I said, the project part of the course, the high level vision part of the course should be covered with under your project. The tentative grading scheme is as follows. So 50% of the grade will be for your assignments, 30% will be for the project and final presentation. So that is like your final exam, and 20% awarded for your quizzes. Okay, so uh, for the project, what I will do is I will like if you've been in my linear algebra, then you know the process. I will just post a number of papers, uh, a few papers that I think are good in the class folder. You can look at them and choose. Or, of course, now that you are, mature enough, you can also go and look for topics that you want to study. Okay, you can also go and look for papers. And if you say, okay, you like this paper, send it to me, and we can talk about it, and if it looks like interesting work, then you can work on it and present it. Okay. So, for example, last year some people said that they wanted to work on GANs because they didn't get enough time in the AML course to look at it. So there was one or two groups working on GAN. So people had like preferences like this also. Okay, there is some part of deep learning they wanted to explore, and they didn't get time in the second semester, so they made it a project in computer vision. So that kind of thing is also fine. Or you can work on something, some algorithm that is state of the art, and try to implement it in some, uh, you know, some off-the-shelf model like few shot learning that is new, transformer that is new. So these kind of things you can sort of pick up an off-shelf model for something, and pick up pick up a data set that seems interesting to you, and then try to add a layer and see what happens. Okay, something like that is also very welcome. Or if you want to read a paper that's already in the literature and you want to implement it, that is also welcome. Okay, classical stuff is also welcome. Some people have done Viola Jones or eigenfaces before. Eigenfaces is more linear algebra, I think. But yeah, Viola Jones, if you want to do a part of it, which is classical stuff. Okay, now nobody uses Viola Jones, but yeah, this is stuff. Ada Boost, for example, is something that you know the understanding gets better if you do Viola Jones. So that is also welcome if you want to do something like that. Okay, so now do you have any questions once you have seen this grading scheme and everything?
Ma'am, I missed one part.
Yeah,
Like project will be a group project, or like we can do it
group
individually.
project. I prefer group project. Yeah, individual is difficult on you and difficult on me because I'm not able to give so much time to individuals. Yeah, so if
Okay.
yeah, so that is it's hard on me and it's hard on you also because then you're the only person probably thinking about it. So if you work in a group, that's easier. Also, we have that way lesser projects to listen to in the end. But that's a joke anyway. What I want to say is, yeah, working in groups is preferred. And I mean, last year I made groups for you. This year, yeah, you can just go ahead and make your own groups. I'm fine with that. So, I mean, today
Yeah.
I'm not expecting that today you will form groups. I think people might be just window shopping today, just to see what the course is and, so not committing. But, and maybe half of the people are in NLP. So I'm not asking you to form the group immediately today, but maybe on Friday we can talk more about this. Yes, somebody was saying something.
Ma'am, regarding the projects, like for the projects we have to do a paper or something like that, or like is that a requirement?
I mean, I just talked about it, right? So there are many options. You can do a paper, or you can pick up some data, some Kaggle competition. You can pick up and do.
Oh, okay, okay. And you said that machine learning is a requirement. So, like, do you mean a machine learning course is a prerequisite or something like that, or like basic understanding of ML is good enough, like neural network?
Basic understanding of ML is not good enough, I would
Okay.
say. Okay, because last year there were one or two students who I accepted this way, and then I couldn't pay much attention, and I thought it was sort of unfair for them. Okay, unfair on the students that they hoped that we would cover deep learning topics and we couldn't really cover, and then
Mm-hmm.
they were sort of dragged through the project. So it is not a good learning experience, I think. So I
Okay.
wouldn't say a basic understanding of ML. No, ML as a course.
Mm-hmm. Okay, okay.
Okay. Yeah.
Yeah.
Any other questions?
So, like, if I haven't taken this, yeah, that probably disqualifies me because I haven't taken an ML course, I guess.
I'm sorry, yes, because you see, you won't be able to get the full thing out of the
Mhm.
course. Okay.
Yeah, yeah, true.
So, yeah. And, then when I have to award a grade, it becomes difficult.
Mm-hmm. Okay.
Yeah.
Yeah, no problem. I'll just take a course next time, I
Yeah.
guess.
Yeah. Exactly. Yeah. Your second
Yeah.
year BSc?
Oh no, sorry, I am third year actually. Oh, I
Okay.
forgot.
Okay,
Yeah.
okay, fine. Yeah.
Mhm. Okay.
But you are welcome to audit. I mean, whenever, I mean, what other than the project, you can listen in the lecture
Mhm.
if you like.
Okay.
Any other questions?
Ma'am, as a prerequisite for linear algebra, do you mean, ma'am, I'm in first year data science, so I haven't done the linear algebra course of yours. So those methods are prerequisites, or do you mean understanding of linear algebra?
Um, so see, I will be freely saying sometimes, okay, you will use SVD here, or here you will use QR, or here you will
Okay,
use RRQR, stuff like that. Okay. So in
Right.
that sense, but yeah, so when I meant linear algebra, I meant linear algebra. I didn't mean numerical linear algebra.
Okay, ma'am. Yeah.
So, but your first year DS, right?
Yes,
You
ma'am.
will have occasion to do this next year. I would suggest you don't do it because for the first year, your core courses are enough.
Okay, ma'am. Yeah.
Yeah, you will get enough work in my course only so that you don't have time to do computer vision.
Okay, ma'am.
Yeah, so next you do it next year. That is what I also then you will have done AML, and then that way you can get more out of this course. ML and AML, right?
Okay, ma'am. Yeah, I'll keep it in mind. Yeah.
Yeah, okay. Yes, any other questions? Okay, so if there are no questions, I'll stop sharing the screen. I will share this file on Moodle, and we can begin with an intro to the course. Okay. So as I said, I'm not doing anything math heavy or technically heavy today. Just introducing you to words and topics. How do I get this to full screen? Control L. Why does it happen that Control L doesn't really work?
Control L for what?
To make it full screen.
I guess like maybe some bug, I guess.
Huh? What should I do? I should double click doesn't work. I just want to make this full screen.
I think there's an option for slideshow or something like that. Maybe like you want to start a slideshow, right?
Yeah.
Yeah, there's a slideshow tab there, and maybe there would be a play button there, like near record. Yeah, near
It's
this
in
slide.
view, I guess.
Sorry. View near record. View.
Yes.
Under view there should be a
No. There's a slideshow button out here. Like
Yeah,
a
this is
slideshow
also
near record. There is slide.
oh here. Yeah, that's right.
Yeah, and now
Slideshow
you can do from beginning or from
from
current.
beginning. Yeah, okay, yes. Thank you so much. All right, there we are. Okay, so yeah, here. Okay, so now here you see this image, right? If you are into computer vision or if you're into photography even, you will immediately see that this is not such a great image because it's blurred. Okay? Even then, when a human sees this or when you look at this image, can you quickly describe what you see in this image?
Cycles, flowers, and flower pots, windows.
Cycles
Yes.
and two windows of
Yes.
flower pots.
Yes. So you just described objects, but you can do more, right? Suppose I ask you, what is this scene about, or what is this image about?
Near a house or something.
That's right. You can say this image is showing cycles and flowers on the side of a house. Okay, there is the sidewalk below. Okay, there's probably a garden behind this, right? So there is so much information. Do you think a computer can do that? That is what computer vision is about. Okay, because when you see this, even though this is a blurred image, you can easily count things in here. You can easily describe things in here. You can easily tell what the shapes, colors of things in here are and what those objects are called. Okay. And this again, you do it in a moment. Okay, you don't need to spend time thinking about this. However, when a computer sees this is what it sees, right? Probably one array if it's a binary image, and probably three arrays if it's a color image. Okay, so but this is what it sees, and from this, we are going to expect it to do all the comprehension that we have done from this image. Okay, and that sort of should give you an idea of how difficult this whole problem is. Okay, how challenging this whole problem is. Okay, for a computer vision pipeline, the first problem itself would be the blurred nature of this image. Okay, um, for example, if you look at this, you can quickly tell me which cycles have baskets and which don't, or how many cycles have baskets here, right? That kind of question you can quickly answer. On the other hand, think of writing a computer algorithm to recognize which cycles have baskets on them. Okay, so it immediately becomes a very challenging problem. Okay, so but anyway, this is the aim of computer vision. Whatever you are able to recognize from this image, you expect an algorithm to recognize and say it like that. Okay, or put it in sentences like that. Okay, and that is what the aim is. And so now this will make you realize that vision is actually a really difficult business. Okay, and just because the human brain is so adept at it, you don't realize it. Okay, and so like there are various things that go into the study of vision. Okay, and computer vision scientists have always been looking at the neuroscience behind vision, and always been uh, motivated by the neuroscience research that goes into vision. Okay, so for example, when if you have seen a newborn baby, okay, and you know anything about the vision of a newborn baby, then you'll know that when the baby is born, they can see only up to 6 inches from their eyes. Okay, so that is the distance up to which they can see. They cannot see anything beyond it. Okay? So if you ever thought that this newborn baby is smiling at me, well, then you're completely fooled, because newborn babies can neither see you nor can they smile at you. Okay? So yeah, but the point is that vision is an acquired training by the human brain. Okay, so it's not that something that comes. I don't mean eyesight. Okay, so there's a difference between eyesight and vision. Eyesight is simply seeing, the eye collecting all the light, okay, and focusing it on the retina. That is simply eyesight. Vision means the comprehension of whatever is focused on the retina. Okay, so that part comes to humans by training. Okay, slowly, the child can start focusing. Okay, then it can start seeing more distances. Okay, by 6 months even, a child can see up to 10 feet of a distance. Okay, the child can focus by 3 months. Most children start focusing on objects. Okay, and this focusing and comprehending that here is an object is itself learning, part of learning of the brain. Okay, so it's no surprise that 1/3 of the human brain is actually devoted to vision, because it is such a complex process. And over the years, neuroscience researchers and cognitive scientists have both made a lot of progress in investigating how our brain processes the raw data that comes in from the retina. Okay, so the brain actually does an amazing job of stitching together. So you are looking at a particular object, and you just move from that object to the right or left a little bit. You don't even realize. I mean, the process is so smooth in your brain that you don't even realize that your brain has to work to stitch together these two views that are coming to it. Okay, that are coming on the retina. So the brain does an amazing job of stitching together all this. Okay, this stitching together is just like your panoramic stitching that came to being, or I think around 2006 or 2007, we started getting this panoramic stitching of images, right? So that comes exactly, I mean, that kind of emulates what the brain does when you move your eyes from one place to the other, okay, or one object to the other. Your eyes also know, the human brain also knows very well what to focus on and what to ignore, right? That is peripheral vision. Your eyes focus on something, and then your brain knows that is what you're looking at, and that is what you want to interpret, and ignore everything else that your eye is seeing from the periphery. Okay, so all these things, these are part of human vision, and these are the things that one wants to emulate in computer vision. Okay, and so like this chessboard example here in the picture, right? Anyone who has played chess ever has no difficulty in recognizing. So, as you know, chess pieces can come in various shapes and designs, right? But I don't think anybody will ever have a problem just because this is a fancily designed queen or bishop. You know, doesn't mean that you won't be able to recognize it. Okay? And a human doesn't take much time, right? Uh, to understand the context that this is a chess piece and it looks like this, so it must be this. This reasoning or this context, this all comes from years of learning, and this is the kind of thing that one wants in a computer vision model. So, for example, this image here, when you see this image, first of all, it is you can definitely quickly describe the situation or the scene in this image, right? But that's not the only thing you can describe. There are more. For example, by just looking at this 2D image, you can tell the texture of stuff. Okay. So, for example, you can imagine what surfaces here might be rough, what surfaces might be smooth, how they might feel. Okay. What the roof might be like. So, you see this roof on the left hand side. So, the roof might look like in real life. Okay. What the flow, what those tiles there on the ground might look like. Okay. You can say, you can also sort of say what is the, you can get the depth perception from this image. Okay. See, as soon as you take an image is clicked, immediately when the 3D object is projected onto a 2D plane, what we have lost is depth, right? There is a loss of dimension. That depth perception you can still do from this image. Okay, so by looking at the image, you can say which car is closer to the observer and which car is farther, which trees are closer and which trees are farther away, right? So this depth perception is something that the human brain can do by looking at a 2D image. Texture perception is something you can do. Okay, so all these, color, of course, okay, color, texture, depth, all these things the human brain is trained to do. On the other hand, you want to teaching a computer to do all these things takes considerable work. Okay, so all these there are these various image processing algorithms that focus on texture, focus on contours, focus on what is called as depth perception. Okay, all these things. So these are also part of computer vision. Okay. Yeah, so these are some of the questions that you can quickly answer. Okay. Whereas this is the kind of thing that you would want an algorithm to answer. So the goal of computer vision, as I've been saying right from the beginning, is to give computers human level perception. Okay, so a typical perception pipeline looks like this. So there is a representation in the form of a 2D image, or it could be frames from a video. Okay, some representation. Then, yeah, you can call it fancy math, and then there is an output. Okay. Now, if you look at that on the top right, if you look at that image, then your brain sort of knows what objects should it be looking at. Okay, what are the objects that it should be picking up from this image? You immediately, your first, your first reaction is, okay, there are 3 cars on a road here, and the road is tree lined. Okay, so that is a very quick description that you can give But when you want a computer to process this, you will have to separate out the objects. For the objects to be, so the human brain does is it separates out quickly, or almost, subconsciously. But this separation has to be done by the algorithm. This is called as segmentation. Okay, so this separation of objects and then recognition of objects. So this is a typical perception pipeline in computer vision. So here, this is what scene understanding looks like. Okay, so you have an image which is fed to some neural network, and then it generates or into an RNN. Okay, so if you want it to spit out some kind of meaningful statement about the scene, then you will be probably using an RNN, and this is the kind of output that you can get. Okay, so the top left image here looks like a simple market scene, right? I mean, it won't take you more than a moment to realize that this is probably a scene from some market. Okay, but again, to make a computer say a meaningful statement about this is an extremely difficult job. Okay. Because when you as a human, because of your years of training that your brain has, it is not, first of all, it's not difficult for you to count the number of people. That is one thing that is very easy for human brain, is to count the number of people in an image. Okay, assuming they are not like hundreds, in which case it might be easier for a computer. Okay, but like with these few people, you can quickly say how many people. You quickly know these are vegetables or fruits, and so you quickly know this is a market. Okay, but each of these things has to be deciphered by the algorithm. Okay, and in some cases you can see in this particular example, some cases the algorithm does quite good. Okay, and how this is done. Okay, so in each of these pairs of images, the left hand image is the original one, the right hand image is showing what is being focused on by the RNN. Okay, so there's a frisbee. Okay, so this program probably detected there's a woman and there's a child and there's a frisbee. Okay, and in the second image there's a dog. Stuff like this. Okay, now so in some cases, yeah, of course, it's done a good job. But now here, look at the bottom left image here. If I ask you what this is, then you will say there's a girl and a soft toy on a sofa chair. Okay. Now the RNN says this is a little girl sitting on a bed with a teddy bear. Most of it is correct. But how difficult would it be for a human to realize that this is not a bed but a sofa chair? Right? This kind of distinction is very easy for a human. On the other hand, this kind of distinction is difficult for a computer algorithm. Okay. Uh, so there are some things like this which are easier for humans and can be difficult for an algorithm. On the other hand, a repetitive task. Uh, so a repetitive task is something that is much easier for a computer than for a human. For example, if you have thousands of objects or bottles, okay, similar looking bottles arranged somewhere, okay, and if you have a clear enough picture of this, it is not difficult to write a computer algorithm to recognize bottles and count it. Okay, and that algorithm will do this counting in a jiffy. Whereas for a human to stand and count exactly how many bottles there are, that is going to be a difficult job. Okay, so you need to understand what is easy for a human and what is difficult. And on the other hand, what is easy in a computer algorithm and what is difficult. Okay, so clearly, if there is a pattern that can be detected and made use of, then that's easy, or that simplifies the work in an algorithm. Okay, so pattern detection and counting, this kind of thing, is sort of uh, more algorithms of this type you will see in computer vision. On the other hand, as I said, detecting something like this, that this is not a bed but a sofa chair, is sort of difficult. Okay. So this is just putting together all the areas that come together to form this field of computer vision, and which is why I say it's a very vast area, and the study of it or designing a course in computer vision, it really depends on who it is being designed for. Okay, so definitely there's mathematics at the base of it all, but there's a bit of neurology or neuroscience. There's a bit of physics that you need to. So neuroscience is something that we will not go into at all, except we will take a good look at the human eye. Okay, but otherwise we will not go into that at all. Physics, we will just try to we will just review ray optics once. Okay, but the other parts of optics, which are incredibly interesting by the way, but we will not be going into that. Then there is this part of engineering. Okay, as I said, there are many things. Computer vision, its use in robotics and so on. But those things we will not go into. The only part that we will of engineering that we will look into is a little bit of this camera basics, because we need to have a basic understanding of how the camera works in order to understand the image acquisition process. Okay. So this we look at that a little bit, and we will be focusing on the computer science part of it. Okay, mathematics and computer science part of it, which means algorithms and machine learning in the end. Okay, so that is what we'll be doing. Although all these computer vision is a sum of all these different areas. This is just a little little peep into various areas that employ computer vision now, and a lot of these are usually taken for granted by us, because now they have become part of our day-to-day life. There's safety, the health industry, of course, security, robots for your comfort, games, and access, of course. Okay, so there are many areas of life now. If you sort of imagine how life was 15 years ago and you want to live it that way, you will find it extremely difficult. Okay, or you'll find some things you just have gotten so used to now that you cannot imagine how it would have been 15 or 20 years ago without these things. Okay. So for example, so how we will not go too much into this optical character recognition, but this is something that is very much in use everywhere now. Okay, so much so that nobody even talks about it now. It's just one of those very old problems in computer vision that have got sort of even your tablet can do this now, right? Optical character recognition, or there are simple apps that do this. So this is a very old problem in computer vision. Face detection is a technology which has come again to our handheld devices even in the past 7 or 8 years. Smile detection, going beyond face detection. Okay, even not just smile detection. Now you can even have some other expressions being recognized, right? Vision-based biometrics. Okay, so this is a very famous and classical example of vision-based biometrics, but now again this is a very common thing, right? Identity cards for not identity cards, but identity in high security facilities is usually done using this biometrics. So logging in without a password, again face recognition. This is also in our homes now, right? Probably your computer already uses this. Object recognition on mobile phones has been there for a while. Okay. This is a sort of old slide, so you see this, but Google Lens and all also has been around for years now. Similarly, iNaturalist, just like uh, Google Lens. This has been around in the entertainment industry for a long time. Okay, this is again part of what I said earlier, computer graphics. Okay, so shape capturing and then using it for special effects. These are more examples. In sports, you see computer vision being used quite widely. Okay, so the example that I'm showing you here, you can find a nice explanation about that yellow line. Okay, so this is quite an interesting read on howstuffworks.com. So, but also, I don't follow cricket so much, but if you follow cricket, you must have seen many uses of computer vision in, even those live telecasts. Medical imaging is by far the area which has encouraged and improved the area of computer vision the most. Okay, medical imaging, right from very old. So this CT scan or MRI scan technologies have been around for a long, long time. Okay, but even now, even the latest technologies that you see in computer vision owe a lot to the medical imaging community. Okay, so there is just so much literature in medical imaging and so many inputs from medical imaging that you can say that more than half of computer vision is about medical imaging. Okay, so image guided surgery is the latest thing in computer vision for medical imaging. By the way, last year, since uh, this detection of COVID through X-rays was a hot topic, some group had also worked on that. But I would discourage that this time unless there is something new to show. Okay, because that topic has been beaten to death now, I think. But there are many other very interesting medical imaging problems that you can look at. Yeah, of course, smart cars. Okay, and Google cars. All kind of interactive games which require object recognition, augmented reality, and industrial robots. So some kind of industrial robots have been around for decades now. Okay, but now there are more advanced robots that are expected to perceive or understand the object that they are seeing, right? Earlier, the industrial robots would just mechanically be doing something, not necessarily looking and perceiving and making a decision. But this ability to perceive and make a decision, that is what is being sought after now, even in industrial robots. Okay, so look at a component, uh, you know, uh, see whether it is defective and make a decision about it, whether it should be in the pipeline or it should be removed. So this kind of decision making, I mean, what I described is probably very naive, but more sophisticated than that. Vision in space, of course, everybody knows about the rover moving around on Mars using vision. So, so the state of the art today is that with enough training data, computer vision can nearly match human vision at most recognition tasks. Okay. Now, the words that you should pay attention here are with enough training data. Okay, that is one huge caveat. And at most recognition tasks, not all yet. Okay, so this, as I said, with enough training data does turn out to be an important hindrance in many computer vision tasks. Okay, first of all, getting good data. You will see when if you ever work on an actual project, getting good data is itself a big problem. Okay, there are many problems in the image acquisition process itself. One has to fix that, and then whatever data that you have got, you have to make it useful enough for your fancy neural network to process. Okay, so if you think that the job of a computer vision scientist is only to design some nice fancy neural deep learning networks and then play around with the layers, no, that is not the business. Most of the work goes in preparing the training data. Okay, and that is tedious work in any case. Okay, and so the success or failure of your model finally will depend on the quality of the data, as is in any data science areas. The same is true for computer vision also. Okay, the only difference is that making data really good in computer vision is a harder task. Yeah, so that is, as I said, the state of the art. There are many recognition tasks that computers have been successful at. Okay, and so we just saw a few examples, but there is much to be done. Here's a brief history, and I mean the sort of the landmark years are listed here, and I'm not going to go through all of them. Just mention a few. Okay, so although this starts in 1959, what I should say that even before 1959, even in the First World War and Second World War eras, uh, the mathematical field of photogrammetry was very much in use. Okay, photogrammetry is the mathematics of measuring, okay, actual distances through photographs. Okay, and this has been used for many years, even before 1959. Okay, so this art of, or the mathematics of photogrammetry is now used in computer vision. Okay. So I should say, I mean, even though it's not mentioned in this brief history, photogrammetry should also be mentioned as sort of the early areas of computer vision, although it was being done by humans at that time. Okay, so I would say 1966, when Marvin Minsky, this is sort of always stated as the beginning of computer vision. He instructed a graduate student to connect a camera to a computer and have it describe what it sees. Now, it will be interesting for you to know that before 1966, when people thought of artificial intelligence and people were working on robotics, it was thought that computer vision is a very simple thing. Okay, people always thought that motion is the more important business, or precision in that area is more important, and computer vision is something that they will be able to just do it on the side. That is what it was thought about as earlier. But when in 1966 this experiment was done, and slowly after that people started realizing that it is not so simple to have a computer describe what it sees. And then well, then this area sort of evolved once the challenges became more clear. Okay. Yeah, and then of course, yeah, there are all these. Yeah, in 2001, it says Viola Jones for face recognition, but before that, there was eigenfaces, which also needs mention because that was sort of the first successful attempt at uh, face detection. Okay. Then you can see, yeah, in 2007, I remember this panoramic stitching. 2006, 2007, Google Photos introduced panoramic stitching, and Google Maps introduced street views. So all those things are also sort of landmarks in the history of computer vision. Among these, what I would, yeah, there are many things written here. And what I would like to stress on is the last three things. Okay, 4 things actually, where uh, this matter of surveillance comes in. Okay, so well, I know that you are. I mean, you're interested in the technical side of things, and we are all working on the technical side of things. However, it is important to remember that there is an ethical side to things also. Okay, and that there is an aspect of the ethics in all this business. Uh, Surveillance, for example, is quite controversial, and so there are how do you say, not directives, what is the word? Uh, each government has its own rules about surveillance or about how computer vision products are being used. Okay, so even if you are not totally into these things, it is advisable to be in the know of what is considered ethical and what is considered unethical in computer vision. Okay, especially in computer vision. This is true in all parts of machine learning, but especially so in computer vision. Okay, because and especially where deep learning is involved. Okay, so I think you must all be aware of what are the controversies or what are the problems that one can that come up in the court of law where deep learning is concerned. Okay, if you have never thought about this, this is an interesting area to look at. Okay, but in any case, whether or not you are too interested in that area, this is something that you should always be aware of. Okay. All right, so this is what I would like to say about the history, and this is some kind of expectation that where computer vision will reach in the next few years. Okay. Yeah, this thing I don't want to say much about. These are just some. So David Marr, this is the book, or this is the person, or this is the computer scientist whose work sort of started the area of computer vision in earnest as a subject or as an area of research by itself. Okay, so David Marr is sort of considered the father of computer vision, you can say, and this is his famous book, Vision. Yeah, this is his philosophy, so I'm not going to talk much about this. We don't have occasion to talk much about all this. But yeah, these are again some of the landmark, how do you say, algorithms that came about in computer vision and that sort of changed the face of the subject. This, which is called as edge or contour detection, was one of it. Segmentation, okay, using graph cuts. Okay, so were you, no. In linear algebra, did anybody do graph cuts last year? I don't think.
Yeah, we did.
Yeah, there
Document
was a group,
clustering.
right? Yes.
Yeah.
So yeah, here it is. Clustering using graph cuts. Okay, so this was one of the successes. Face recognition, of course, and this particular one is using Viola Jones. SIFT, which has been around in digital image processing for a long time. Okay, SIFT, which is shift invariant feature transform. So this is a huge. I mean, this algorithm is now used just everywhere. Okay, and so this was also a major contribution to this area. This I will not talk about right now. This spatial pyramid and all, but histogram of gradients again. This I'm showing this picture because it just these green lines are gradients. Okay, and that is why this is called a histogram of gradients. And it turns out to be very useful in what is called as pose estimation. Okay, for example, this problem of pedestrian recognition. Okay, you have if you have an image and you want to see how many people are walking or how many people are there in this image, that kind of thing. So in that kind of problem, the histogram of gradients. So this is also a very, important success in the field of computer vision. So now what a little in the remaining whatever 3-4 minutes, I want to talk about data sets. Okay, so as I said, getting good image data for your neural network is a difficult job. But there have been various data sets made publicly available over the past few years that have simplified job for researchers as well as learners who are learning this. Okay, so you must be aware of some top image data sets like ImageNet, GoogleNet, or the COCO data set and so on, right? So Pascal VOC in 2007, this was the first such data set that came up, okay, which contained only like 20 object categories. But then ImageNet came, ImageNet was announced, and ImageNet, actually the word stands for two things. It stands for this data set, which contains of 22,000 categories and 14 million images. Okay, and but it also stands for this challenge, okay, which is this ILSVRC, which stands for image. What is it? ImageNet Large Scale Visual Recognition Challenge. Okay, so ImageNet stands for both these. So this image classification challenge was announced for these 1,000 object classes and these many images long ago. So this was 2014 even. Okay. But ImageNet, even now, is used, as one of for if you want to use any of these off-the-shelf models, and if you want to use the ResNet or any of these neural networks, then as a backbone for training, many of these models will use ImageNet. Okay, because it has so many images of so many different categories. Okay. However, in quality, okay, what happened? Oops. Oh, so this was my last slide. Okay, so I do want to say one or two things. More than the ImageNet images, the open images in Google, which was released in 2016, is considered to be a better, better in the sense. It also depends on what you want to use it for. It's considered to be a nice data set because, well, it contains around 9 million images, but those images are not of single object. They are complex scenes which span thousands of classes of objects. Okay, and moreover, there are 2 million hand annotated images with bounding boxes. As you will realize, this having annotated images with bounding boxes and all, this is extremely important for your training data. Okay, so this Google's open images has lots of those images. Okay. Even this COCO data set, which was used in the segmentation challenge, has many. COCO means common objects in context. Okay, so again, that is a very useful data set for scene understanding, that kind of thing. So there are many of these image on Kaggle, of course. Every time a challenge is posted, a data set is posted with it. So there are, you know, I mean, data sets that will be useful for various kind of tasks. Okay, by the way, one of the applications that was not mentioned here but is very much in vogue now is drone image classification or drone image recognition, or analysis of drone images, which means the images are taken with a drone and then you want to analyze them, or satellite image analysis. Okay, so that is one thing that I forgot to mention in this whole area, which is a very important application of computer vision. And even for those kind of problems, there are many data sets available. Another major area of application of computer vision is in agriculture now. What is this area called as precision agriculture? Okay, you can tell various things, and this has been around even from the time that satellite imagery became available. But now with drone imagery, it has sort of, you cannot book a satellite to say, okay, tomorrow I want the picture of my field to be taken by this satellite. Okay, that you cannot do that. But with drones, this kind of technology has become more available and easily applicable by even the common farmer. So that is a huge and upcoming area, especially in India. Okay. Yeah, all right. So that was my little introduction to what computer vision is about, and I hope I have answered questions about how the course is going to proceed. So if you have any more questions or any comments to add, you are welcome to do so. Yeah, what is Shivli asking me? We can make our own annotations. Yes.
Yeah,
You mean
ma'am,
preparing?
actually, yeah, I'm replying to Shankaram. Sorry,
Ah,
mistakenly message you directly.
oh, sorry. Okay. Yeah. Is there any question you would like to ask or make a comment or anything? Otherwise, we can stop. And we will start in earnest on Thursday. And so, in the beginning, as I said, when in the image formation business, it will be a little math heavy, in the sense linear algebra heavy. But then later, when we get into algorithms, we don't require all those that geometric language.
Ma'am, is the undergrad course in linear algebra at CMI enough?
Sorry, say it again.
Is the BSc Algebra 1 course enough for this?
In the B, I will have to ask what. So there was a revision in courses, and I don't know if do you do linear algebra in algebra 1?
Yes, yeah.
Yeah. So linear algebra wise, that should be enough. I think you do eigenvalues, eigenvectors, eigenspaces, and
Yes,
Jordan canonical form, spectral theorem, these kind of things.
yes, ma'am, yeah.
Yeah. So yeah, linear algebra wise, that is the thing.
Hello, ma'am.
Yes.
Ma'am, the assignments are going to be like, can we do it in groups of 2 or 3, or is it?
Yeah. So yes. So assignments. This has always been my policy, right? Even in linear algebra, you can do everything you want to do in groups. You can discuss. You're free to share ideas and everything. When you finally write down the answer, it should be your own. That's the same policy here.
Okay.
When you finally do the coding, because otherwise you don't learn. Okay? You don't develop your style. You don't learn. And what is the point then of doing this whole? It's a sham otherwise. If you're going to copy each other's answers. Okay. So yeah, so the policy is the same, that you can discuss, share ideas. You can, of course, it is useful to discuss in groups. But when you finally write down the answer or solve the assignment and submit it, that should be your own work,
Hmm.
coming out of your own understanding.
Okay.
Yeah.